In this episode, we are building one of the most useful mental models a new analyst can have, which is a clear understanding of how a system is put together and how that system normally behaves over time. A lot of people try to learn cybersecurity by memorizing alerts, attack names, and defensive terms, but that approach only gets you so far if you do not understand the environment those things are happening inside. System-level behavior and architecture fundamentals matter because suspicious activity only looks suspicious when you have some sense of what the system is supposed to be doing in the first place. If you can picture how users, applications, services, memory, storage, and network activity fit together, then an investigation starts to feel less like guessing and more like following a pattern. That is especially important for the CompTIA cybersecurity analyst, CYSA+ learner, because so many exam scenarios assume you can reason about what a system is doing without needing to touch the system directly. A simple place to begin is by separating two ideas that beginners often blend together. Architecture is the design of the system, which means the major parts, the relationships between those parts, and the way work is supposed to flow through them. Behavior is what the system actually does over time, including how it starts, what it runs, what it accesses, how it communicates, and how it responds to users or other systems. Architecture is closer to the blueprint, while behavior is closer to the daily activity happening inside the building. That distinction matters because a secure design can still behave in unsafe ways if it is misconfigured, overloaded, or misused, and a noisy system can still have a clean underlying design. Analysts need both views. They need to know what the system was meant to be and what it is actually doing now, because the space between those two things is often where trouble first becomes visible. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At the most basic level, every system is trying to coordinate resources so useful work can happen in a stable and repeatable way. The Central Processing Unit, CPU, handles instructions and calculations. The Random Access Memory, RAM, provides fast temporary workspace for active tasks, and storage keeps data and software available over longer periods of time. Those parts sound simple when described one by one, but their interaction is where system behavior starts becoming meaningful. A system under ordinary load uses the CPU, RAM, and storage in ways that match its purpose, whether that purpose is handling email, running an application, storing files, or supporting a web service. When a process suddenly consumes far more memory than expected, or when disk activity spikes at odd hours, or when the CPU stays busy for reasons nobody can explain, those changes may become useful clues. A beginner does not need to become a hardware expert, but it helps to see these resources as the physical and logical foundation of everything else the system is doing. The operating system, OS, sits on top of that foundation and gives the rest of the environment structure. The OS manages hardware access, schedules work, tracks users, controls permissions, organizes files, and provides the common environment in which applications and services operate. That is one reason analysts care so much about it. The OSouth is often the place where system behavior becomes visible in a useful way because it records account actions, process launches, service changes, network activity, and access decisions. A normal user may see only windows, applications, and documents, but an analyst sees the OS as the traffic manager that decides what runs, what is blocked, what starts automatically, and what leaves a record behind. If you understand the OS as the coordinator of system behavior rather than just the thing that makes the computer usable, then many cybersecurity events begin to make much more sense. Inside the OS, one of the most important concepts is execution. Programs do not merely sit on a drive waiting forever. They are loaded, turned into running processes, broken into smaller units of work, and given time on the system according to rules the OS is enforcing. That matters because a security incident often becomes visible through execution behavior rather than through some dramatic warning message. A process starting from an unusual location, a child process launching under an unexpected parent, or a service appearing where it should not exist may all point toward misuse or compromise. The analyst's job is often to compare observed execution to expected execution. What should run on this system? Which account should launch it? When should it start? What other processes should it interact with? Once you begin thinking this way, the system stops feeling like a single machine and starts feeling like a set of coordinated activities that can be understood, measured, and questioned. Memory behavior adds another layer to that understanding because a system does not only reveal itself through files and visible programs. While activity is happening, data, instructions, connections, and credentials may exist in memory long before or long after they become obvious anywhere else. Analysts care about memory because active threats may live there, tools may unpack themselves there, and useful evidence may appear there only for a limited time. This is one reason live systems can tell a different story than stored files alone. A process may look ordinary on disk, but behave very differently once loaded into memory. A compromised system may show running code, network sessions, or injected activity that would be hard to explain if you only looked at the file system after the fact. For a beginner, the important lesson is not to memorize every memory term. It is to understand that the system has a live working space, and much of the most meaningful behavior exists there while the system is active and disappears once that activity stops. Storage and file organization matter just as much, because systems leave behind a great deal of evidence in the form of files, settings, logs, and scheduled activity. The file system is how the OS organizes what is stored, where it lives, who can reach it, and what changed over time. Analysts care about file paths, permissions, creation times, modification times, and whether software or scripts are running from places that do not fit the system's usual pattern. They also care about persistence, which is the idea that a program, service, or malicious tool may arrange to survive restarts and remain active over time. A suspicious startup item, a changed service configuration, or a hidden scheduled action can all make more sense when you remember that the system is not only storing data. It is also storing future behavior. That is a very useful way to think about architecture. Some system components describe what exists now, while others quietly shape what will happen the next time the machine reboots, the user signs in, or a task reaches its trigger point. Networking pushes this conversation outward because systems are rarely isolated. Most of the time, they are sending, receiving, requesting, responding, and depending on communication with something else. A client system may talk to an identity service, a database, a cloud application, a file server, or an external site. A server may handle requests from hundreds or thousands of users, or it may quietly support a single application behind the scenes. System-level behavior, therefore, includes not only local activity, but also the pattern of who talks to whom, how often, in what direction, and for what reason. When analysts describe a system as beaconing, reaching out unexpectedly, accepting unusual inbound traffic, or making requests to unfamiliar destinations, they are really describing behavior against an architectural backdrop. The behavior matters because communication patterns reflect purpose. Once you understand what a system is supposed to connect to, it becomes much easier to notice when that same system starts acting like it belongs to a different role altogether. Users, accounts, and privileges form another essential part of architecture because systems do not simply run tasks in a vacuum. They run them in the context of identities and permissions. A user account, a service account, and an administrative account each exist for different reasons, and their expected behavior should be different as well. This is where trust boundaries begin to matter. A system may trust a certain account to read a file, but not to change core settings. An application may be allowed to talk to one internal service, but not to every server in the environment. When behavior crosses those boundaries without a clear reason, the system is telling you something important. A beginner who understands privilege at a practical level gains a real advantage, because many incidents are really stories about an identity doing more than it should, going somewhere it should not, or operating with a level of authority that does not match its role. Architecture helps define those boundaries, while behavior reveals when they are being stretched, broken, or bypassed. Applications and services add still more depth because most modern systems are part of larger chains of dependency. A web application may rely on an identity provider, a database, an external application programming interface, API, and a logging service, all while presenting itself to the user as one simple experience. That matters because system behavior often reflects those hidden relationships. A slowdown in one supporting service can create strange behavior somewhere else. A failure in one dependency may cause repeated retries, error messages, or unexpected network patterns across several systems. A compromise in one application layer may lead to suspicious activity in another because the systems trust each other in normal operation. Analysts therefore need to think in terms of components and dependencies rather than in terms of isolated boxes. The more connected the environment becomes, the more important it is to understand what each system depends on, what data it exchanges, and which failure or compromise paths are possible because of those normal design relationships. Modern architecture also includes abstraction, which means the system you are analyzing may not map neatly to one physical box sitting in one room. A virtual machine, VM, can behave like a full system while sharing hardware with many others. A cloud-hosted workload can scale, move, or restart in ways that look very different from a traditional on-premises server. A containerized service may appear and disappear quickly while still performing important work inside a larger application design. The fundamentals still matter, though. Even in modern environments, something is executing code, using memory, storing data, enforcing permissions, and communicating across networks. What changes is the level at which those activities are managed and observed. For a beginner, this is good news rather than bad news, because it means the basic mental model still holds. Systems may be more distributed and more abstract than they used to be, but architecture still defines roles and relationships, while behavior still reveals whether those roles and relationships are being used as intended. Resilience is another architectural idea analysts should understand, because the design of a system affects not only how it behaves when healthy, but also how it behaves when stressed, attacked, or partially broken. A well-designed system often includes redundancy, segmentation, fallback paths, and controls that limit the blast radius of failure. A poorly designed system may depend too heavily on one component, trust too broadly, or expose too much of itself to direct access. This matters because suspicious behavior and operational instability are not always separate stories. A system under attack may fail because it lacks resilience, and a system with weak architecture may make investigation harder because one compromised component can affect everything around it. Analysts benefit from seeing architecture as more than a map of connections. It is also a map of consequences. If one identity service fails, what else stops working? If one server is compromised, what other paths open up? Those are architecture questions, but they directly shape what system-level behavior will look like during both ordinary operations and real incidents. Visibility ties everything together because none of these concepts help much if the system does not generate useful evidence about what it is doing. Logs, telemetry, resource metrics, service states, configuration changes, network sessions, and authentication records all help analysts understand whether the system is behaving normally or drifting away from its intended role. This is where baselining becomes powerful. A baseline is not the fantasy that nothing ever changes. It is a grounded understanding of what kinds of change are expected, what patterns usually appear, and what counts as meaningful deviation. When analysts notice a new service, an abnormal login pattern, a process chain that does not fit the system's purpose, or unusual communication after a software update, they are comparing observed behavior to that baseline. Good architecture supports that work because it makes roles clearer. Good visibility supports it because it makes evidence available. Together, they give analysts a much stronger chance of distinguishing routine system life from activity that deserves concern. One common beginner mistake is to think of architecture as static and behavior as purely technical, when in reality both are shaped by business purpose. A finance system behaves differently from a developer workstation because it exists for a different reason. A public-facing application has different communication patterns from an internal reporting server because its job is different. If you ignore purpose, then behavior can seem strange when it is actually normal, or seem harmless when it is actually risky. Another common mistake is assuming that more complexity always means better design. In truth, complex architecture often creates more dependency, more hidden trust, and more opportunities for weak visibility unless it is managed carefully. Good analyst thinking therefore stays grounded in a few simple questions. What is this system for? What should it normally do? What other components does it rely on? What identities should interact with it? Where would unusual behavior most likely appear first? Those questions turn architecture and behavior into tools for reasoning instead of just topics for memorization. By the end of this discussion, the main thing to carry forward is that system-level behavior and architecture fundamentals give you a working map for understanding security events. Architecture tells you what the system is, what parts it has, what relationships it depends on, and where trust boundaries exist. Behavior tells you what the system is actually doing right now, how that activity compares to expectations, and whether something important may have changed. When you can hold both of those ideas at once, alerts become easier to interpret, investigations become easier to follow, and suspicious activity becomes easier to explain in plain language. That is why this topic matters so much for a developing analyst. You are not just learning how computers are built. You are learning how to see the difference between design and activity, between expected use and dangerous drift, and between a system that is simply busy and a system that is behaving in a way that deserves real attention.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.